Hello students, welcome back to the series Coordination Chemistry. In this module, we will be discussing about the trans effect and its applications. So, this is the last module of the series. With this trans effect, we will be concluding the series Coordination Chemistry. And now we have to study what is trans effect. See, in the last module I have discussed about what is I have given introduction to the trans effect. So, this trans effect it was first identified by Werner and Chernow in 1926. So, these two scientists identified this trans effect in 1926. And this trans effect, it is mainly based on the platinum based complexes, that is platinum based coordination complexes. And now what is trans effect? It is a labilization of the ligands which are trans to certain other ligands having trans-directing nature. So, what is really trans effect is all about the labilization of the ligands which is trans to certain trans-directing ligands. First identified by Chernow and Werner. And now the reaction, the trans effect, the reaction involving the trans effect is kinetically controlled reaction, since in this reaction thermodynamically stable products are not always formed. So, it is an electronic effect. Now, while discussing about trans effect, initially we will be starting with the complex PT, the synthesis of PTNH3 twice Cl2. How can we synthesize this complex? It is a platinum based complex, it is a square planar complex, that is PTNH3 twice Cl2. It can be prepared either from PtCl4 or from PTNH3 4 times. See the reaction sequence. Initially, if I take PtCl4 as the initial compound, if I am adding ammonia ligand to this complex, this ammonia will be substituted, and again if I add one more ammonia molecule, the product will be a cis complex, that is cis PTNH3 twice Cl2. It is the product is a cis isomer. And if I start with the platinum PTNH3 4 times 2 plus and adding Cl minus ligand, I will get a trans isomer or a trans PTNH3 twice Cl2. So, the products are different if I take the reactants, different reactants. These two different reactants give different products. And the reason is that the trans effect is the reason for the formation of two different products. I will be discussing in detail in the coming slides. And the product formed depends on the trans-directing ability of the ligands in the complex. In the first reaction, Cl minus, first reaction it was PtCl4 2 minus complex. In the first reaction, the Cl minus has a greater trans-directing property than the ammonia. So, Cl minus is having a greater trans-directing property. That is why we get a trans isomer. In the second reaction, since Cl minus has a greater trans-directing property, a cis isomer is formed. The concept will be clear. I will be clearing the concept in the coming slides. So, initially you have to understand that why the two different products are formed. It is due to the different trans-directing property of the ligands present. Okay. And this trans effect, it was Longford and Gray. They arranged these several ligands based on the decreasing order of their trans-directing ability. It was Longford and Gray. They arranged the ligands based on their trans-directing ability. And what is then they arranged these ligands in a particular order, and that arrangement is generally, it is called as trans effect series. So, what is trans effect series? The series in which the trans-directing ligands are arranged in the increasing order of their trans effect. It is called as trans effect series. Who arranged, who were the scientists, which were the scientists who all were involved in such such a process? The Longford and Gray, they arranged the ligands based on their trans-directing ability. Okay. And now you can see the series, how they arrange the different ligands based on their ability. You can see that F minus, that is fluoride ligand, F minus is having the least transdirecting ability, and Cn minus or Nc, that is Nc minus or Cn minus, it is having the greater transdirecting ability, and in between you can see several ligands arranged, that is the least for F minus, followed by OH minus, H2O, NH3, Py means pyridine, Cl minus, Br minus, I minus, etc., etc. So, you have to study this arrangement of series, this arrangement of ligands in a particular series. This series is called as Transeffect series. Okay. And now the Transeffect was explained by two different theories. The first theory is called as the Polarization Theory, and this Polarization Theory was put forward by Grinberg. It was Grinberg who put forward this theory, that is Polarization Theory. It is the theory tries to explain the sigma bonded complexes, sigma bonding, the trans effect that affect the sigma bonded complexes. So, what is the theory? The polarization theory, it is based, that the platinum, we are discussing about platinum based complexes. Here I have written the platinum complex, that is PT, L2, T and X. Why I have written T and X? T means that ligand, T ligand is having the transdirecting property, and X is the leaving ligand, and if the initial complex is reacting with the entering ligand Y, the product is PT, L2, T and Y. See, X is being removed, Y is being entered into the complex. So, this is a general reaction, and now how he explained the polarization theory? See, consider this is how the polarization theory is all about. We have the platinum metal as the central metal atom. Platinum is there at the center, and you have the transdirecting ligand named as T. You have the leaving ligand named as X. Okay, and this platinum is able to polarize the transdirecting ligand. The thing that is to be kept in mind is the directing ligand is highly polarizable ligand. It is a highly polarizable ligand, which means that platinum is able to distort the electronic arrangement inside the transdirecting ligand. Okay. And now you know that platinum has got the positive charges here, and this the positive charge of platinum is able to polarize the transdirecting ligand, and as a result of polarization, see the positive charges accumulated here, and as a result the negative charges, it will polarize the transdirecting ligand T, and negative charges will be accumulated here. And since positive charge is accumulated in this side towards the transdirecting property, transdirecting ligand, the other side of the central metal atom will be negatively charged. Then what happens? We have the leaving group X is there, right? The X minus means they are having excess of electrons present in the X minus ligand, and these electrons will be, they will be repelled by this platinum. As a result, platinum X, PT-X bond will lengthen, which helps in the easy removal of the X minus ligand. That is how the polarization theory explains the trans effect. Again I repeat, what happens? We have the central metal atom is platinum. We have the transdirecting group or transdirecting ligand there, which is named as T, and we have the leaving group which is named as X. Okay, and this platinum is able to polarize the easily polarizable transdirecting ligand T. As a result, negative charges accumulated here and positive charges accumulated near the this side of platinum, and finally you have the negative charges of platinum which is accumulated here this side, which will be repelled by the excess electrons present in the leaving group, thereby increasing the platinum X bond length and which results in the easy removal of the X minus ligand. This is how the trans-directing ligand helps in the easy removal of the ligand which is trans to that ligand. And now this is how polarization theory. And now second theory, we have second theory, that is pi bonding theory. This theory always explains the pi bonded ligands, the trans effect of the pi bonded ligands. It was proposed by Chad Dunganson and Benani in 1955 and Orgel in 1956. So, these were the scientists involved in the pi bonding theory. It considers, this pi bonding theory considers the trans effect of pi bonding ligands. We know that pi bonding ligands are CO, CN, etc. and the trans directing property of this pi bonding ligands are explained in the pi bonding ligands are explained in the pi bonding theory. And what is pi bonding theory all about? According to the pi bonding theory, we have the pi star orbital of the ligand. Pi star means anti-bonding orbital of the ligand that accepts the electrons from the metal orbital, because it is a it is a pi bonding ligand. CO, CN, etc. are pi bonding ligand. They will be accepting the electrons from the metal orbital. To where they are accepting? They are accepting the electrons to the pi star orbital. Okay. And now what happens? This way a metal ligand pi bond occurs. How the metal ligand pi bond occurs? They will be accepting electrons from the metal to the pi star orbital of the pi bonding ligand. And now the electron density, what happens then? The electron density of the metal on the side of the back bonding pi bonding ligand increases. So, since the electrons are accepted by this pi bonding ligands to the pi star orbital, the electron density between metal ligand bond, between there will be an high electron density, thereby increasing the electron density between the metal and ligand. What is the result? Thereby that will decrease the electron density which is towards the ligand that is opposite to this pi bonding ligand. So, this result in the diminishing of electron density trans to the back bonding ligand. Okay, then diminishing electron density diminished means what will happen? That bond will break very easily. Okay, I repeat, what is pi bonding theory? It explains the pi bonding. It explains the trans effect of the pi bonding complexes or pi bonding ligands. For example, CO, CN, etc. are pi bonding ligands. What happens initially? What happens? They will accept the electrons from the metal to their pi star orbital and thereby increasing the electron density between the metal ligand bond. There will be the higher electron density, and what is the result? That will decrease the electron density trans to the back bonding ligand, and that ligand which is trans to the back bonding ligand will be easily removed. This is how pi bonding theory explains the trans effect. Okay. This helps the incoming ligand to coordinate to the metal trans to the metal ligand pi bond to form the pentacoordinate transition state, and this is now it explains the mechanism, that is it forms a incoming ligand, it facilitates the incoming ligand to enter the complex and forming the product. Finally, it will lose the leaving ligand to form the product. That is what happening. Okay. And now we have to understand, which is a very important part of this topic, that is applications of trans effect. We are moving to the applications. So, what we have studied, what is trans effect, what are the different theories that explain trans effect. We have two theories, polarization theory and pi bonding theory. And finally, moving to the applications of trans effect. First application is the synthesis of cis and trans plating. Cisplatin is a very important compound which is used in the cancer therapy. So, the synthesis is very important. So, first application is the synthesis of cis and trans plating. We have discussed this reaction in the previous slide, because cisplatin means cis PT NH3 twice, cis PT NH3 twice Cl2. This is the cisplatin, and transplatin means trans PT-NH3 twice Cl2, that is it. And how can we synthesize cisplatin? If I start with the complex PtCl4 2 minus, and if I add ammonia ligand, NH3 ligand, if I add, what happens? Initially this ammonia ligand will be replacing Cl minus, one of the Cl minus, and we will get the product like this. Okay. And now if I am adding again ammonia ligand, what happens? If I am adding again ammonia ligand, now here comes the trans effect, the importance of trans effect. I have to consider which ligand has the greater trans directing property. If I consider, if here we have to consider how many ligands, what are the types of ligands involved? It is Cl minus and NH3. So while we are comparing ammonia and Cl minus ligand, which ligand is having the trans directing property, more trans directing property? It is Cl minus. Just have a look at the trans effect series. See, Cl minus is having the greater trans directing property when compared to ammonia. So Cl minus is able to direct the incoming ligand trans to its position. And now what happens? See the reaction. The Cl minus and ammonia, which is more having the trans directing property, it is Cl minus. That is why this ammonia is coming cis to this ammonia. Already we have one ammonia molecule being substituted here, and now coming ammonia will be entering at the cis position, because this Cl, rest you have 3 Cl, and either this ammonia will be coming here or here. If it is here, it is cis. If it is here also, it is cis. The same compound is there. No, I repeat. First we will be starting with PtCl4 complex. I am adding ammonia molecule, and one ammonia molecule is being substituted here, and again if I add one more ammonia molecule, what happens? I have to consider the trans effect, ability of the trans effect, which is having the greater ability, it is Cl minus. So this Cl minus has the ability to direct the incoming ammonia to the trans position. So this Cl, if this Cl is considered, this ammonia will be, coming ammonia will be attached here, or if this Cl is considered, the coming ammonia will be attached here. If it is attached here or if it is attached here, the same product is formed, that is the cis isomer. The cis isomer is a product. Okay. Now next example, that is if I start with the PtNH3 4 times 2 plus complex. Initially if I am adding Cl minus, it will be just substituted, that is one ammonia, it will be replacing one ammonia molecule, and chloride Cl minus will be substituted there. And now if I am adding one more Cl minus, what happens? Now I have to consider the trans effect of the ability, trans directing ability of the Cl and ammonia, which is having the greater trans directing ability. It is Cl minus having greater trans directing ability when compared to ammonia. Then what happens? This Cl will be weakening the ligand which is trans to the Cl, which is trans to the Cl means this ammonia will be replaced, and I get this Cl being attached here. Now I get the trans product. Okay. So the main thing you have to understand is that the trans ability of the ligand should be considered while substituting any ligand. Before that you have to study the series correctly, the series of the trans effect series should be studied thoroughly, then only you can understand the reaction sequence. Okay. So this is how the synthesis of cis and trans plating take place. And now here is another example. If I take a general ligand, if I represent the ligand, if I represent the central metal atom as M, generally I am representing, I have a 4 Cl minus ligands there. It is a square planar complex. One of the reaction, that is if I am adding ammonia ligand, what happens? One Cl minus will be replaced by one ammonia, and I will get the product like this. And now if I am adding another ligand, NO2 minus is added to the complex. What is the determining factor now? I have to consider the trans-directing ability of the ligands already present. Which are the ligands present? It is ammonia and Cl minus. And which is having the greater trans-directing ability? It is Cl minus having greater trans-directing ability. And now what happens? The Cl minus, this Cl minus, either the incoming NO2 will be attached here or here. If it is attached here, I will get a product like this. If it is attached here, also the same product, it is just reverting, no, the same product is there. It can be attached here, NO2 can be attached here or here. Okay. So, this is the product. And now, if the reaction is initially started with NO2 minus ligand, what happens? See the reaction sequence. First, one Cl minus will be replaced by NO2 and I will get the product like this. If I am adding NH3 ligand to that, now the situation is different, because NO2 minus, I have to consider the trans directing ability of the ligands already present here. Which are the types of ligand? It is NO2 and Cl minus, which is having greater trans directing ability. See, NO2 and Cl minus, NO2 and Cl minus, it is NO2 here, Cl minus. So, NO2 is having the greater trans directing ability. And now coming to the reaction, NO2 is having the greater trans directing ability, means this NO2 will be weakening the ligand which is trans to the NO2. So, it will weaken the bond MCl bond which is trans. So, now the incoming ligand ammonia will be entering this position only. Why? Because of the greater trans directing ability of NO2 minus. I hope you understood the concept. And now explaining another reaction. See, we have PTCl4 2 minus, that is again 4 Cl minus ligands are there. You have C2H4 as the ligand. And now initially what happens? This C2H4 is being attached, or it is replacing one Cl minus and attaching to the platinum complex. And now if I am adding an ammonia ligand, now what is the thing to be considered? The trans directing ability of Cl minus and C2H4 minus. If I look at the, if I investigate, if I look at the trans effect series, I can understand that C2H4 minus is having the greater trans directing ability. Then what happens? The C2H4 will direct this incoming ammonia trans to its position. Now this Cl minus will be weakened and the ammonia ligand will be attached here. I will get a trans isomer. And now the second example, that is if I start with the PTCl4 2 minus and if I am adding ammonia ligand, what happens initially? This ammonia ligand will be attaching to the one of the position, or it will be replacing one Cl minus. Okay. Then I will get the product like this. And now if I am adding C2H4 ligand, that is initially I am adding ammonia ligand, it will be just substituted anywhere. And now the second time if I am adding the second ligand, that is C2H4 to this complex, what happens? Here now we have to consider the Transeffect series. Comparing this ammonia and Cl minus, this ammonia and Cl minus when considered, you will have the Cl minus having greater trans directing property. And now either the C2H4 can be attached either to this position or this position. If it is attached to this position, I will get the cis isomer. If it is attached to this position also, I will get the cis isomer. See, either position, if the incoming C2H4 is attached here, I will get the cis Cl2, because this Cl and this Cl will be in the cis position. If it is attached here, this Cl and this Cl, the same product is same. So, the cis isomer is formed if I am adding C2H4 in the second step. This is how the applications of Transeffect is there. That is, we can synthesize cis and trans isomer depending upon the ability of the ligands to direct to the trans position, which is very important in the applications of Transeffect. Initially, what have we started with? The synthesis of cis and trans platin. We have to consider the trans directing ability of the existing ligands in the complex before we are considering the attack of the ligand. So, the trans directing ability of the ligand will be controlling the position of the incoming ligand. That is the main thing that is to be kept in mind. Okay. So, in this module we have studied the trans effect and what are the theories that explains the trans effect and what are the applications of trans effect, which is very important. The applications of trans effect is very important because it involves many synthesis of cis and trans isomer. We have to consider the trans directing ability of the incoming ligand, and before that you have to study the trans directing series. Trans effect series has to be thorough clearly. Okay. And now the applications of trans effect, cis and trans platin is a very important compound that is to be considered, because I have already told that cis platin is used in the cancer therapy. So, that is one example. Many examples are there explaining the trans effect, that everything will be it is all, I think it is understood, it is clearly understood by the examples which I have taught. And now with this I am concluding the series coordination chemistry. Hope you all understood the topic coordination chemistry, or I hope you are benefited by this series. Thank you all for watching the video. Thank you.